This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome everybody to section 5.4, day 1 of properties of logarithmic functions. So I'm going to start off with just saying here, if you've got the log of 100 times 10, I don't have to tell you that 100 times 10 is 1,000. And if you want to find, if 1,000 is the power, 10 is the base, you would need an exponent of 3 to get there from 10 to 1,000. So log of 1,000 is 3. Similarly, you could say that log of 100 is 2, and log of 10 is 1, and 2 plus 1 is 3. So check this out. You can actually say that log of 100 times 10 is equal to log of 100 plus a log of 10. Let me show you what that looks like with some other, this same structure, different multiplication. So log 2 base 8. So if 2 were the base and 8 were the power, the exponent you would need to get from 2 to 8 would be 3. Log of 2 base 8 is 3. Log of 2 base 4, log of base 2, 4 is 2. And if you add 3 plus 2, you get 5. Similarly, you could say that 8 times 4 is 32, and what exponent do you need to get from 2 to 32? You need 5. 5 is equal to 5. So you can say that the original two expressions are also equal to each other as well. Log base 2 of 8 and log base 2 of 4 is equal to log base 2 of 8 times 4. What we basically have is we have multiplication on the inside, and then we've got addition on the outside. And that holds here also. Multiplication on the inside, addition on the outside. 9 times 9 is 81. The log base 3 of 81 is 4. 3 to the 4th is 81. And 3 squared is 9. 3 squared is 9 here. 2 plus 2 is also equal to 4. So you can say that 4 is equal to 4. Even more importantly than that, you can say that log base 3 of 9 times 9 is equal to the log base 3 of 9 plus the log base 3 of 9. Addition on the outside, multiplication on the inside. So what would that look like here? We've got base 10 of x times y. Multiplication on the inside becomes addition on the outside. In general, you could say something that we call the product rule, log of base any base a of m times n, multiplication in the middle, will equal log base a of m plus log base a of n. Multiplication on the inside, addition on the outside. So expressed as a sum of logarithms, well, you could multiply 9 times 27, and that would give you a very large number. You would get 243. But what I'd actually like to do is express it as a sum, following the instructions, express it as a sum of logarithms. You can take multiplication on the inside and turn it into addition on the outside. You've got two different logs, a sum of logarithms. Log base 3 of 9, log base 3 of 27. Well, what exponent would you need to get from 3 to the what power gives you 9? 2. 3 to the what power gives you 27? That would be 3. And I know this isn't, what I've boxed right here is actually the answer. This is the answer. You don't need to go any further, but I do want to show you that 2 plus 3 is equal to 5. And here, if you said the 3 to the what power gives you 243, that would be to the 5th power. Expressed as a sum of logs. Here, we can only do this really making sure that if, and maybe I should have also said that here, making sure that you've got the same base each time. Here, you can only use this rule if the bases are the same. Log base 2, log base 2, fine. Addition on the inside, multiplication, addition on the outside, multiplication on the inside. Okay, so let me show you some more properties. Check this out. If we try to figure out what log of 8 to the 4th would be, well, we don't really yet know how to deal with exponents on the inside of a logarithm. So let's just change the exponent into multiplication. We know how to deal with multiplication on the inside of a logarithmic function. If this is 8 to the 4th, we just write it out 8 times itself 4 times. And now, if we have multiplication on the inside, it becomes addition on the outside. That would be log 8 plus log 8 plus log 8 4 times. Now, if you wanted to group that all together, we can just say that it's 4 times log 8. Similarly, let's say it's at 5. Well, you could do the same exact tricks, just 5 times. 8 times itself 5 times. And then you're adding log of 8 to itself 5 times and collecting them all back together. Again, you get 5 times log of 8. The pattern that I'm starting to see here is that you're going to take the exponent and move it out into the front. An exponent on the inside would be multiplication on the outside of the log. Log base 2 of 5 to the third, that would be 5 times 5 times 5, or just 3 log 2 to the of 5. Same pattern holds here. Log of 6 squared, that would be log of 6 times 6. And it's the same trick over and over again. You might as well just jump straight from here down to here. You can take this 2 as an exponent and move it out in front. An exponent on the inside becomes multiplication on the outside. So I want you to try this here. What would log base a of x to the 9 be? And you don't have to write it out. You can just jump straight to the answer if you're recognizing the pattern. The pattern, as you can see here, would be log of any base a of any power m to the p. You can relocate that p from the inside, if it's an exponent, to the outside and make it multiplication. In words, basically it says exponent inside becomes multiplication outside, or multiplication outside becomes exponent inside. You can go back and forth. So express each of the following as a product. Here's the product. It's the product of the what used to be the inside exponent is now outside product, and you don't have to change anything else. Here we have to remember that taking something to the 4th root would be raising it to the 1/4 power. So then, as soon as we see we have an exponent, we can move the exponent out in front. 1/4 times log of a of 7. Log of x to the 6th would be 6 log x, moving the exponent out in front. And that's what we have. Here's something new we haven't dealt with yet. We've dealt with multiplication on the inside and exponents on the inside, but we haven't figured out exactly how to deal with fractions or division. But if we change it to exponents, if we change this division or this fraction into some sort of an exponent, then we know how to deal with it. We're just going to take this 8 to the -1, which is the same thing as 1/8, and we're going to move this -1 out in front. It becomes subtraction. It becomes a minus or a -1 out in front. This is -1 times log of 8, or just negative log of 8. Same thing here. We don't know how to deal with division exactly yet, but we can change this into 6 times 1/7, or 6 times 7 to the -1. And now, although this seems a lot easier and less confusing, this version is composed here of nothing but multiplication and exponents, which we actually know how to deal with. We can say that the multiplication on the inside becomes the addition on the outside, and an exponent on the inside becomes a multiplication on the outside, which is confusing. But if you recognize this right here, it actually it's the same thing as subtraction. Adding the opposite becomes subtraction, log of 6 minus log of 7. Compare that to the original, and you might start to notice that division on the inside looks a lot like subtraction on the outside. You can apply the exact same trick here. We had 4/5, and that's the same thing as 4 times 1/5, or 4 times 5 to the -1. Multiplication on the inside becomes addition on the outside. Exponent on the inside becomes multiplication on the outside. And then this all becomes just subtraction. Log of 4 minus log of 5. Log of 4 minus log of 5. There it is. That's the same thing as log of 4/5. That is right here. 4/5 is the division right here that you see in this fraction becomes subtraction. And that's going to be the pattern that we hold. Log of x over log of x over y becomes log of x minus log y. The pattern is stated right here in the quotient rule of the logarithm. Log of any base a of m over n becomes log of base a minus log of a n. To put it in words, division on the inside becomes subtraction on the outside, and they can go back and forth between each of these. So, wow, look at this crazy logarithm. Log of base z of x squared times y to the fifth, all divided by z to the fourth. Well, you can take this you can do it in multiple steps, or I'm just going to do it all in one step. I see an exponent, I see multiplication. This 2 becomes this 2. This 5 becomes this 5. This 4 becomes this 4. And we have addition here because I see addition, and we have subtraction here because it's in the denominator, it's being divided. It's the x times the y divided by the z. The division becomes subtraction. And in many cases, you'll be able to see, if you wanted to, I mean, you can show work like this. You can have circle this and have an arrow, circle this and have an arrow if you want. Circle this and have an arrow. That's one good way to show work. There's some more work to show in this particular case because 4 log z of z can actually be simplified. These, if you have log z of z, it simplifies down to 1, so it becomes 4 times 1. So this is the final finished answer. We're going to combine these all to be, combining all these rules again. Anytime you see a square root, cube root, fourth root, it's just a lot easier to write it as an exponent, particularly in this section, because we know how to deal with exponents. We don't necessarily know how to deal with, there's no rules that deal with square roots or roots in general. But if we convert it to exponents, we know how to deal with exponents. And in fact, before we use our rules here, I'm just going to combine some of these exponents together. I'm going to distribute this 1/3 to the 2, this 1/3 to the 1, the unwritten one, and the 1/3 to the 5. So we've got a to the 2/3 now, b to the 1/3, c to the 5/3. And now we're going to use our logarithms, properties of logarithms. And so we've got multiplication on the inside. That becomes addition. We've got division, or fraction bar, on the inside. That becomes subtraction. We've got an exponent, bring it out front. An exponent, bring it out front. An exponent, bring it out front. I see 1, 2, 3, 4 different factors on the inside. They're going to become 4 different terms on the outside. And each of these is going to be log base b, same base. We have an exponent 5, bring it out front. An exponent 3, bring it out front. An exponent 4, bring it out front. These notes brought to you today by chromium. It's the 24th element on the periodic table. That's not this table. This table is just meant to summarize the logarithmic properties. I did a Google search and I found this. It seemed to fit exactly what we're looking at. We've got the property is the product property, and inside the log you've got multiplication that translates to outside of the log addition. Inside the log is division, outside the log becomes subtraction, and it goes back and forth. You can manipulate these, and you can collect all the terms together, or you can spread them out as you wish. You can, if you're given outside the log, you can translate that to inside the log, or go back and forth. The power rule is the same thing. Inside the log, if you see any kind of exponents, that translates to outside of the log multiplication. Anyway, I'd like you to start assignment 5D1, copy the problem list, and do the first problem, and I'll see you in class.